Tutorial 7. In this tutorial, we're going to introduce one-way ANOVA, or one-way analysis of variance. We're going to talk about checking assumptions for one-way ANOVA, the different sources of variation, and the F-statistic. So in the last tutorial, we talked about bivariate analysis with one quantitative outcome variable and one qualitative explanatory variable that has two levels. And we discussed the different tests that we would use when the groups of the qualitative explanatory variable are either dependent or independent. So if the two groups consist of exactly the same people, so repeated measurements under different conditions, then they're most likely dependent. And in this case, we would use a paired t-test if our data meet the necessary assumptions. Or we would use a Wilcoxon signed rank test if they don't. If the two groups compared contain totally different people, then they're most likely independent. And in this case, we would use an independent or a two-sample t-test if the assumptions are met, or if not, we would use a Wilcoxon rank sum test. So this week, we're going to be talking about inference with a quantitative outcome variable and one qualitative explanatory variable that has three or more independent groups. So first we'll talk about the parametric form of analysis in this situation, which is known as one-way analysis of variance, or one-way ANOVA. So one-way ANOVA is actually an extension of the t-test. And so if we run this test on a qualitative variable consisting of just two groups, we'll actually get the same results for the most part as we did with a pooled two-sample t-test. So one-way ANOVA has similar assumptions to the pooled two-sample t-test, as we'll discuss in a few minutes. In one-way ANOVA, the null hypothesis is that all means are equal. So in other words, there's no difference in the means of the three or more groups, populations, or treatments being compared. So the mean of group 1 equals the mean of group 2, which equals the mean of group 3. The alternative hypothesis is that at least one group's mean differs from the others. So as with the other statistical tests that we've talked about so far in the course, we begin a hypothesis test by assuming that the null hypothesis is true, that there is no difference in the mean between the groups, and then calculating a p-value that tells us if our null hypothesis really were true, how likely would it be that we would see a sample statistic deviate from the hypothesized value by as much or more than we did merely by chance. An important note about ANOVA is that this test will only allow us to conclude either that we don't have enough evidence to believe that there is a difference in means, or we have evidence to believe that at least one group mean is different from the others. But we cannot conclude from ANOVA alone which specific group mean or means differs from the others. In order to determine which groups are significantly different, we need to use multiple comparisons, where you make all possible pairwise comparisons. So compare group A to group B, group A to group C, and group B to group C if there were three groups. And we can do these multiple comparisons using a method known as Bonferroni's, or we can use Tukey's or Dunnett's tests. But I'm not going to go into detail about these in this tutorial because we're only just introducing ANOVA, and we're going to talk more about this next week. But essentially, these tests allow you to reduce the likelihood of a type 1 error. So first, let's talk about the assumptions for ANOVA. So for the most part, this is the same set of assumptions that we had for the two-sample t-test with equal variances. The sample was selected through a simple random sample. Observations within groups are independent. The different groups, populations, or treatments compared are independent. And each group set of observed values comes from a normal distribution, or there are large sample sizes for each group. And finally, that the variation in each group, or the variation of individual observations about the group-specific mean, is approximately equal. So this means that we're assuming that the true variations of individual observations around each population group mean is approximately equal. So how do we check that these assumptions are met? To verify that the first three assumptions are met, that the groups are independent and observations within each group are independently and randomly sampled, we need to have knowledge of the study design. So we check these in the same ways that we have with the other tests that we've discussed so far in the course. If participants or observations were sampled through a simple random sample, and the groups being compared with our explanatory variable each contain totally different people, we can assume that the first three assumptions are met. To check the normality assumption, we either need a large sample size for each of the groups being compared, so greater than 20 as a guideline, or we can look at box plots or histograms of the observed values for each group, or something called a QQ plot. The histograms and box plots should look fairly normal, and QQ plots should look fairly linear if the data really is normal. If a QQ plot is not normal, S-shaped or large curvature will appear. To check the assumption of equal variance, also referred to as constant variance, we can take a look at side-by-side box plots, or just compare the estimates of the sample standard deviations. As long as the largest group standard deviation is not more than double the smallest standard deviation, we can assume that the variances are equal in the population. So if we see that the size of the boxes, so the interquartile range of the box plots for the groups, are roughly the same, and the ranges are also pretty similar, we can assume that the variation in each group is roughly the same for the population. There are two sources of variation used in one-way ANOVA calculations: between group variation and within group variation. So first let's talk about between group variation. This is the variation that is due to differences in groups. This is what's known as the explained variation. This tells us how far each group mean moves from the grand mean. The grand mean is an average of all of the individual observations in all of the groups. A range of different terms are used to describe the between group variation. It's sometimes referred to as the mean squares between, or the mean squares for the model, treatment, or regression. The second type of variation is the within group variation. This is the variation that is random, or the unexplained variation. This tells us how far individual observations move from a group mean. And the within group variation is also known as the mean squares within groups, the mean squared error, or the mean square of residuals. So this slide shows a visual example of the total variation, within group variation, and between group variation when four groups are being compared. Remember that with one-way ANOVA, we are assuming that the variation is the same across groups, and that under our null hypothesis, all groups have the same mean. So let's first discuss the plot on the left. This shows the total variation of all observed values from each of the four groups around the grand or overall mean. This shows us individual observed values and how they vary around the grand mean, which I mentioned is the average of all of the individual observations in all of the groups. This total variation can be broken down into two parts: the within group variation, which is shown in the middle, and the between group variation, which is shown on the right. The within group variation tells us how far individual observations move from a group mean. The horizontal lines for each of the four groups represent the mean of each group, and the dots are the individual observations. The between group variation tells us how far each group mean for each of the four groups moves from the grand mean. If the variation of the group means around the grand mean is large relative to the variation going on within a group, this suggests that there may be a difference in the population means of the groups. In other words, if the between group variation is large relative to the within group variation, this suggests that there may be a difference in the population means of the groups being compared. So here's a different way of plotting the same thing. Here we have the four groups being compared, and based on these four groups, we can calculate the grand mean, the average of all of the individual observations in all of the groups. We can also calculate each group's mean. We can then determine how far each group mean from each of the 4 groups moves from the grand mean. This between group variation is represented by each of the 4 red lines. This tells us how much of the total variation can be explained by the group differences. The blue lines show the within group variation, or how far individual observations move from a group mean. This tells us how much of the total variation occurs within a group and is unexplainable. If the between group variation is large relative to the within variation, this gives us evidence to believe that there may be a difference in the population means of the groups. The formulas for the between and within group variation are shown on the right. And this is a little boring to describe, but for the people who feel like the formulas are a little bit daunting, I'll just break it down about what these actually say. So to calculate the between group variation, for each group we subtract the grand mean from the group mean and square this. We then multiply this by the sample size of the group. We do this for each group and add them together, and then divide this by the number of groups minus 1. The within group variation is just like the pooled variance that we saw with the 2-sample t-test with equal variance. You multiply the sample size of each group minus 1 times the variation in each group. You do this for all of the groups, add these together, and divide this by the total sample size, the total number of observations for all groups, minus the number of groups. So with one-way ANOVA, our null hypothesis is that the means for each of the groups are equal. As with other tests that we've discussed so far in the course, we assume that this null hypothesis is true when calculating our p-value. If our null hypothesis really is true, that all groups, populations, or treatments have the same mean, then we would expect the variation within to be the same as the variation between groups. But if the between group variation is large compared to the within group variation, this suggests that there may be a difference in the population means of the groups. And we can actually test this using an F-statistic, which is a ratio of the variation between to the variation within groups. The F-statistic is a little different from the other test statistics that we've discussed so far in the course, in that it has a degrees of freedom associated with the numerator and a degrees of freedom associated with the denominator. The between group variation has a degrees of freedom of the number of groups minus 1. This is the value in the numerator of our F-statistic. The within group variation, the denominator, has a degrees of freedom of the sample size minus the number of groups. The larger the F-statistic is, or the larger the between group is to the variation within groups, the more evidence we have to suggest that the groups differ. For example, if our F-statistic is 10, this means that the variation explained by group differences, the variation between groups, is 10 times the variation that is unexplained, or the variation going on within a group. If there's no difference in the means of the groups being compared, so our null hypothesis is true, then the F-statistic will equal 1. We also know that with sampling variability, even if there really were no difference in the group means, our test statistic may be larger than 1 merely by chance. So we can use our F-statistic to get a p-value. And this p-value will answer the question, what is the probability of obtaining a test statistic equal to 10 or larger merely by chance, given that our F-statistic equals 1, which means that all group means are equal. If our p-value is less than our significance level, which is usually 0.05, we reject the null hypothesis and conclude that we have evidence to believe that at least one of the means is different from the others. Remember though, ANOVA only allows us to conclude that either we don't have evidence to believe that there is a difference in means, if we fail to reject the null hypothesis, or we have evidence to believe that at least one mean differs from the others if we reject the null hypothesis. If our data doesn't meet the assumptions necessary to conduct one-way ANOVA, we instead use the Kruskal-Wallis test. The Kruskal-Wallis test is a non-parametric test for the equality of the median of 3 or more groups or treatments or populations when the groups are independent. It is a non-parametric alternative to one-way ANOVA. The null hypothesis is that there's no difference in the medians between groups, and the alternative hypothesis is that at least one group median is different from the others. The Kruskal-Wallis test works with ranks of the observed values rather than the actual values themselves, and therefore it frees itself from making assumptions about the distribution of the observed values. It's pretty much identical to one-way ANOVA, but with the data replaced by their ranks. It's an extension of the Wilcoxon rank sum test for 3 or more groups. Since it's a non-parametric method, this test does not assume a normal distribution, unlike one-way ANOVA. However, it does assume an identically shaped and scaled distribution for each group, except for any difference that may exist in medians. Okay, so here's an example problem. Suppose the National Transportation Safety Board wants to examine the safety of compact cars, mid-size cars, and full-size cars. It collects a random and independent sample of 3 for each of the car types. Using the data provided, test whether the mean pressure applied to the driver's head during a crash is equal for each type of car. Assume a significance level of 0.05. What is the null and alternative hypothesis? What questions do we need to ask? What test do we use? Calculate the appropriate test statistic. Do you reject or fail to reject the null hypothesis? And interpret the p-value. So first of all, what are the null and alternative hypotheses? The null hypothesis is that the mean pressure applied to the driver's head during a crash test is equal for each type of car. The alternative hypothesis is that at least one mean pressure is not equal. Next, what questions do we need to ask? We need to check to make sure that our data meets the necessary assumptions for one-way ANOVA, since 3 independent groups are being compared. We know that it's a random and independent sample, and that the 3 groups are different, since each is based on a different type of car. So our first 3 assumptions are met. So we need to check for normality of data, and we can do this with a box plot, histogram, or a QQ plot. These side-by-side box plots show the distribution of the data in each group. We can see that the data for full-size and mid-range cars is fairly normally distributed. The data for compact cars is somewhat skewed, so it's not perfectly normally distributed. But something to keep in mind is that checking this assumption is arbitrary if you can justify that you assume the pressure during a crash to be normally distributed based on prior knowledge. And also, 2 of the 3 groups are normally distributed, so it's fair for us to assume that the assumption of normality is met. We then test the assumption of equal variances, so we can see that the largest group standard deviation is not more than double the smallest standard deviation. So it's okay to assume that the variances are equal in the population. So this is just a side note showing you what normal and non-normally distributed data looks like when using a histogram, QQ plot, or box plot. The normal distributions are shown on the left, and the non-normal distributions, in this case skewed to the right distributions, are shown on the right. As you'll know, a normal histogram is bell-shaped, while a non-normal one is not, so it's skewed to the right in this case. A normal QQ plot has a straight line, whereas the QQ plot on the right is curved, which suggests non-normality. The box plot on the left is normally distributed, so the interquartile range and range are symmetric around the median, whereas on the right, the whisker on the top, showing the range, is much higher above the median than below the median. Okay, so back to our problem. Based on all the checks we've done, we can assume that the data approximately meets our assumptions, so we determined that we can use one-way ANOVA in this case. The next step is to calculate the appropriate test statistic, which in this case is the F-Statistic. So this is the code that we would use in R for this, or we could do this by hand. And here are our results that we would get from R. So our mean squared between, or between group variation of 43,025 divided by our mean squared within, or within group variation of 1709 gives us an F value of 25.18 with an associated p-value of 0.0012. The next question was, do you reject or fail to reject the null hypothesis? Since our p-value of 0.0012 is less than 0.05, we reject the null hypothesis and conclude that we have evidence to believe that at least one of the means is different from the others. And the final question was, interpret the p-value. So we would say that given that the mean pressures for the cars are equal, the probability of obtaining an F-statistic of 25.18 or more extreme merely by chance is about 0.12%. Here's another example problem. In a genetic inheritance study, random and independent samples of individuals from several ethnic groups were taken. The data is shown below. Conduct a hypothesis test to compare the ethnicity variable with respect to the mean sister chromatid exchange variable. Assume a significance level of 0.05. In this example, only two groups are being compared. So we would use either a two-sample t-test, or if the assumptions for the two-sample t-test aren't met, we would use a Wilcoxon rank sum test. So here's a little bit of a spoiler alert, but in this case, we would use a Wilcoxon rank sum test because our data don't meet our assumptions, as I'll explain in a minute. So our null hypothesis is that the medians of the groups are the same, or the median difference equals 0. And the alternative hypothesis is that the median difference does not equal 0. Based on the information provided, we know that our data meets certain assumptions for one-way ANOVA. The data are selected from a simple random sample, so we can assume that the observations were independently and randomly selected. And we know that the groups are independent since people are either in the Caucasian or Asian ethnicity group. But if we plot the data in side-by-side box plots, we can see that the data are not normally distributed. The distribution of the Asian group is highly skewed, and there are also some outliers in both groups. So we conduct the Wilcoxon rank sum test in R, which gives us a W statistic of 16 with an associated p-value of 0.1142. Since the p-value is greater than our alpha of 0.05, we fail to reject the null hypothesis and conclude that we do not have evidence to believe that there really is a significant difference in the medians of MSCE between Asians and Caucasians. So I just want to finish the tutorial with a quick summary of key interpretations. We've already gone over this quite a bit in the course, but p-values don't really have the most intuitive interpretation, but they do have a very precise interpretation. So I'm going to cover it again for those of you who still might find this a bit unclear. So if you're asked to interpret a p-value, the general interpretation would be, given that the null hypothesis is true, there is a probability of X of observing a sample mean that you got, or more extreme, merely by chance. And this interpretation will differ a little bit depending on the test you're conducting, but this is the general format. And remember that this interpretation of a p-value is different than the conclusion you make based on your p-value for your hypothesis test. For a hypothesis test interpretation, if the p-value is less than your alpha, You reject the null hypothesis and conclude that you have evidence to believe that there is a difference in the means. If your p-value is greater than your alpha, you fail to reject the null hypothesis and conclude that you don't have enough evidence to believe that there is a difference in the means. For a 95% confidence interval, your interpretation would be, we are 95% confident that the true mean of one group is somewhere between an interval higher than the other group, or we are 95% confident that the interval lower limit to upper limit covers the true mean difference. So that's all I have for this tutorial. In the next tutorial, we're going to talk about multiple comparisons, and we're going to go over some example problems.